Hi, Deepak. Yeah,
Hi.
so Deepak is not currently a student. He's a PhD graduate recently,
Yeah.
couple of months ago. So yeah, and he graduated from Syscon. Currently working at Dot Robotics, and here at Dot Robotics is leading efforts in productizing and existing robotic prototype into a scalable and deploymentable product. And his professional interests include multi-agent systems, robotics, autonomous systems, and distributed intelligence. Beyond his technical work, he is deeply interested in Indic knowledge systems and Hindustani classical music. Great. So we should have a session by you sometime on your classical music too. Yeah. His work reflects a blend of rigorous engineering, product thinking, and a continuing engagement with India's intellectual and cultural traditions. Okay, Deepak, you can start by sharing your screen, and I assume that you'll be giving talk on your work at IIT Bombay during your PhD. That's what I'm
Yes.
assuming.
So,
Okay,
yeah, I
sure.
mean, yeah, sorry.
Please go ahead and share your screen.
So, I think my data screen should
Yeah,
be
we can see
visible.
your screen,
Okay.
not the talk yet. Yeah,
Is it good?
I can see your talk. Yeah,
Yeah. So, I'll begin.
yeah, you can. Thank you.
Thank you, sir. Also, thank you, Yogesh, for inviting me to do this presentation. Yeah, the previous talk was a bit technical, I believe, compared to what will be mine. So, I'll be talking about multi-agent patrolling. The questions, few insights based on my work during my PhD and like, the contributions to my PhD. So I did my PhD, like Sandeep mentioned, in Syscon, IIT Bombay, under Professor Karthikasan and Lena Olsen. Yeah. So what is patrolling? Everybody should be familiar with police patrolling, but just for the sake of completeness, so patrolling is the repeated visitation of important locations in an environment for it can be for surveillance, monitoring, or deterrence. So why do we do this? So critical infrastructure requires monitoring for faults and anomalies. Uh, Certain sensitive environments require surveillance. These can be some, let's say, cantonment area or defense establishments. Uh, so we cannot observe all things at all times, right? And hence, uh, we need some sort of agents which are mobile and go around monitoring these sort of setups. Okay. Then the question is why do with a single agent, um, improve revisit frequency as well as the coverage. Coordination, yeah. So then the challenge is how do you have these multiple agents go about these environments? So that's where the algorithmic design comes in. So you need to coordinate these agents so that uh, the areas are not, the effort is not duplicated and all the area remains visited. So by design, it can be such that may require more frequent visits than others. Yeah, just for non-IITB people, this campus that you see on the left is a portion of IITB. So some uh, black dots are represented here as nodes, and road network is taken as the graph. So yeah, the central challenge with multi-agent patrolling is how should a team of agents coordinate their motion so that important locations are revisited frequently while so while visiting these important locations, the entire environment should also be not ignored. So more formally, the case that I was interested in is such campus-like environments. So it can be city blocks or closed campuses like our own campus or certain cantonment areas, airports and such. So these campuses being modeled as graphs. So junctions and important buildings can be the nodes of interest, and edges are the uh, road networks or the pathway between these nodes. Uh, so the edges are weighted by the time taken for traversal. So in my work, I'm assuming that all of this is given. So I'm not bothered with how these edges are traversed, but all right. And the assumption is multiple agents move continuously on the graph. A subset of all the nodes are treated as priority locations. With they can have certain other constraints. So objective again is to design the agent's route so that locations are revisited frequently with greater attention given to the priority locations. Okay. In terms of, uh, please feel free to stop me whenever if anybody has any clarification. I'll keep going. I mean, I'm talking to a screen, right? Yeah. So how do we measure the factual performance? So there is this term used in the literature by the community called idleness. So idleness is essentially the time for which a node has been left unvisited. So on every visit, it's reset to zero, and then as the agents uh, go away from this node, leaving it unvisited, the idleness keeps on increasing. So yeah, small idleness is great, but not possible for all locations. So with priority nodes, what we did is we had a constraint called time period. So the require, I mean, time period Ti for the node Vi. So the requirement was that the idleness of node Vi should remain within Ti for all time. So that is with priority nodes. Is the problem difficult? Okay, infinite horizon. The first thing is with coverage, you can say that this problem sounds similar to coverage. But for graph coverage, it's a one-time exercise that you need to cover the entire graph. Whereas over here, by design, the problem is uh, an infinite horizon one, where we need to keep on visiting the locations in fact indefinitely. Uh, yeah, as the size of graph as well as number of agents increase, the number of possibilities in terms of routes scales up exponentially. So that brings in the combinatorial complexity. Yeah, coordination we already discussed that agents should avoid unnecessary overlap and all the regions should be visited. So yeah, with priority locations, there is this competing requirement that the overall uh, campus or the overall environment should be visited, while you also need to satisfy some constrained nodes. So plus there are certain practical constraints like strategies must be computable and you should be able to do this in a uh, finite memory and compute, right? So the this sort of motivated us to take up this path that can an effective finite horizon patrol strategy be represented by a finite repeating structure. The idea is if you can get some sort of a decent finite structure, which you can then repeat, it addresses, I mean, it basically reduces your search space. Okay, so in terms of how people have gone about approaching this problem, the first thing is what we just discussed. That's the recurrent. Let agents repeatedly follow some sort of cycle. Second is you partition the graph. I mean, each agent gets a partition. How do you go about doing this partition? It can be through various ways, like people have done with having uh, sort of equal clusters or have partitions such that the cycles in those partitions are same. Uh, yeah, but each agent gets a partition and then the agent carries out a cycle over that partition. Then there are certain reactive approaches where you keep track of idleness during deployment, and these are online strategies where the agents decide on the go. Like when they arrive at a node, they decide which neighboring node to go to next. And then, I mean, more recently, there have been certain learning-based approaches where people have trained neural networks and other weight matrices to uh, like a priori to deployment, and then by deployment, you're basically uh, deploying that model. So yes, all these are essentially addressing on how to uh, arrive at a solution which is practical and deployable. But the existence of a solution itself is still an open question. whether an optimal infinite horizon patrol strategy so exists is an open question. Yeah. So first one, I just in terms of questions that remain regarding existence, I just mentioned: does an optimal patrol strategy exist? If it does, what structure would it have? Could recurrence be recurrent strategies be an optimal? If not optimal, then near optimal. And okay, all this is good. Can such strategies be computed and deployed efficiently? So again, central theme of the research was to convert the infinite horizon patrol problems to finite recurrent ones so that it can be implemented in practical scenarios. So, okay, in terms of my research, what we did was we started off with single agent, try to achieve certain results in with a single agent case, then went into general multi-agent scenario, and then suggested certain practical algorithms. I'll go a bit over each of them. Okay, so with single agent priority patrol, the way we define the problem is so we are given a graph and a subset of them is priority nodes with a common time period T. We need to find a patrol strategy such that idleness of those priority nodes are within the time period, while non-priority nodes are also visited repeatedly. So this is essentially a constraint satisfaction problem. The first thing that we had to establish was whether this problem is feasible. I mean, if whether it is well defined. So, I mean, you can't keep arbitrary time period values, right? So we achieved a lower bound on the feasible time period, and then showed that existence of a recurrent. I mean, there exists a recurrent strategy for every feasible instance. So the optimal uh, strategy is of the recurrent type for this problem. And we then gave a constant factor approximation algorithm that gave a strategy within 2 times t. So if you give me a graph, let's say ITB campus, first thing would be like what is possible in terms of the time period. So we answered that, and then also gave a strategy which uh, did execute the task with at most two times the time period. So that those were the insights from single agent, and then we thought of more generalizing it into the multi-agent setup. So with multi-agents, the problem was slightly broader. So as I said, with single agent, it was a basic constraint satisfaction problem. Whereas over here, we had an objective. So we were trying to minimize this J pi. So pi is the patrol strategy. Uh, so given a set of agents and a graph, the objective is to minimize J pi. J pi can be different idleness functions. So it can either be minimizing maximum idleness, minimizing weighted maximum idleness, where weights, I mean, each node can have a 0 to 1 weight depending on its priority. And it can be an average, or and then we also had the constraints on the subset of nodes, the parity nodes, right? So in general, be written as a p-non, a weighted p-non of idleness vector. So for this objective, what we achieved is an epsilon optimal recurrent strategy exists. So that is, we can find a pi r, which is recurrent, with the cost being 1 plus epsilon times the optimal. And I mean, you need to realize the constraints on priority nodes as well with 1 plus epsilon. But you can find a recurrent strategy which achieves epsilon optimal performance. So you, yeah, the idea was that you start off with an arbitrary feasible strategy. You can discretize it, find uh, a portion of the strategy which you can then repeat infinitely often, right? So you can construct a recurrent strategy for any arbitrary feasible strategy. And the proof is a bit longer, but the core idea is since every strategy can be mapped onto a recurrent strategy and the set of with I mean epsilon drop in performance, so you have an epsilon optimal recurrent strategy. Why recurrence? Because in general, so if strategy can be of any form, right? Any kind. That like if you want
Deepak,
to
just
describe that
wanted to give a
strategy,
heads up about 5 minutes, like maybe.
sure, I've got a couple of
Cool.
2 or 3 slides.
Thanks. Yeah.
Yeah. So yeah, in general, with infinite strategies, since it's infinitely long, it's impossible to describe it. Uh, yeah, yeah, it will also have a unbounded search space in terms of how do you find an optimal strategy. And you can all, I mean, there is no standard way to compare it with other class of strategies. So, for example, people have suggested algorithms that are meant for beat coverage or uh, cycle covers as uh, solutions to patrol problems. How do you compare it with the optimal strategy? You don't know, right? So, with our result, we show that there exists a recurrent strategy which is near optimal. Uh, yeah. So the last part of the work was okay. So far, whatever I spoke of was talking about the nature and class of solutions itself, right? So in terms of practical deployment, how do we go about this? So we came up with an idea that since we were going with this priority locations, priority nodes concept. So we can look at the walks between priority nodes. So that would reduce the search space. So all the walks between priority nodes were considered in the first approach. And this was an offline algorithm where you stored all the walks. And then during deployment, you looked at a cost function, which was a function of idleness. So based on which you assign the next walk, which took you to another priority node. So what we achieved was it performed better than the off the shelf strategies which were not concerned with priority nodes. So that did show that there is a requirement to design an algorithm specifically addressing this problem. But the issue over here was you cannot populate all the walks between.
Hi, Deepak. Yeah, we lost you. I think you're muted.
Yeah. Is it good?
We don't see your screen.
Okay.
Yeah, we can see the screen. Maybe you can tie it up in two
I
minutes.
was
Yeah.
as on this
Now it's
slide,
good.
right?
Yes.
So I covered the time period based patrolling.
Yeah, I
So
think that was done. Yeah.
yeah, okay. So continuing, so the issues over there was I don't know if you would catch that. So the set of walks keeps growing as the graph size or the set of priority nodes keeps growing, and it grows exponentially. So uh, in order to address that, we came up with this notion of rabbit walks, which wherein we introduce a tunable parameter where based on your memory you could uh, increase the number of walks that you store and then go about like during the deployment it doesn't change much. You are still doing it based on the real-time information on idleness that you have. Uh, okay, so in terms of from our work, the key takeaways are priority-based patrolling was something that we introduced in our work. So it is a useful framework because like in real life, and this we validated uh, during our conversations with defense agencies as well. I mean, they were interested in such problems. Second point, I mean, this is regarding the problem formulation itself, that priority-based patterning is useful. In terms of results that we achieved, recurrent, and the third was finite walk-based strategies. We could scale it to larger practical situations. Uh, yeah, in terms of open directions, which are still to be worked upon. So in our work, we assumed homogeneity in terms of what agents can do. Uh, Agent failures weren't considered. Dynamic, dynamic both in terms of dynamics as well as agent dynamics weren't considered. And what happens when you have, so this is under non-adversarial setting, right? So where you are operating as a deterrent. It's not to eliminate an already existing threat. So how do you look at the problem when you have an adversary in the environment is still an open direction. Yeah, so the takeaway from my our work would be the search for arbitrary infinite path trajectories can be reduced to structured recurrent strategies and practical finite route assignments. Yes, that is me.
Thank you, Deepak. It was a nice talk. So now we are open for the questions. If audience has any questions.
So let me ask a quick question there, Deepak. Thanks a lot. Nice talk. By the way, is anyone hasn't raised their hand, or I mean, hope I'm not jumping in.
I can go after you.
Okay, all right, all right. So Deepak, a quick question for you. So it's a very interesting problem. So one thing that you've shown is that you can get to within epsilon, I mean, kind of some, I mean, that epsilon optimal result was with arbitrary epsilon, right? So you can get some
Yes,
recurrent
yes,
path. Okay,
yes.
all right.
So
But all right. But do you have like a bound in the time of compute? Like, for example, can you guarantee that?
okay, so we didn't show how to get the strategy there. We just showed the existence. So
Okay, okay, all right. So I mean, so I'm assuming that
yeah,
in the absence of
it does
constructive.
shoot up. I mean, it's still exponential. I mean, so that's essentially a discretization constant. As you make it smaller and smaller, the uh, possible strategies, the set of possible strategies do shoot up.
Okay, okay. And so I mean, when you showed the existence here, but just out of curiosity, did you make use of any constructive procedure as part of the existence? So it might have been like, you have some part where you assume that something exists, but part of it relies on a constructive result. So I'm just sort of wondering
Yes.
whether
So
if you did, that's where
correct.
that's one source of sort of algorithmic complexity, right? Sorry.
So in terms of the proof, so what we showed is any arbitrary feasible strategy has a epsilon recurrent strategy. So that
Okay.
mapping exists. Now, set of recurrent strategies is finite, and hence the epsilon optimal plane. Now, in terms of how do you go from arbitrary feasible strategy to an epsilon version of it, that is, I would say, in the order of the strategy that you supplied. So we essentially need to extract out a recurrent portion, right? So I mean, depending on the epsilon, you will again, I mean, the compute would change that, but it it would change linearly with that.
Okay, okay. And I suppose there was one final question about this. So, I mean, one of the, I mean, obviously here I'm assuming that two robots can't traverse an edge simultaneously, right? Is that an assumption that you've made anywhere?
No, 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 none of it.
Ah,
So
okay,
I mean, the only assumption is so the pattern strategy representation is the node agent and time. That's the index that we have. So you can have multiple agents, in fact, stay at a particular node and stuff like that.
okay, okay, okay. Understood. All right, great. Okay, all right. Yeah, thanks, Deepak. Sandeep.
Hi, Deepak. Are there any other questions? I can wait. Okay, quick question. So here, even your like the amount of time you wait for, or idleness is what you call, or the frequency of
Yes.
revisits, right? So these
Yeah.
idleness, these are fixed timings, right? Like or the threshold is fixed, even for the priority nodes.
No, okay. Idleness is essentially a variable.
Sorry, can you repeat?
Did I
I think
lose
we
you
missed.
again?
Yeah, yeah.
Uh,
Can you
is it
repeat?
okay if I turn off my camera? Maybe the link is bad.
Yeah, I can turn off mine too. Yeah, tell me.
Yeah. Yeah. So what you're saying is the idleness is a variable with time. So
No, I know, but
yeah,
your threshold, like idleness, kind of goes on increasing, but it's a
correct.
fixed rate, right? It's at fixed rate for all the nodes.
Yes. So that's the time.
So
Yeah.
can I,
Idleness is
if I need to change my patrolling path, uh, so let's say that like some nodes are more important currently, but some other nodes might be important after 1 hour. So how can I change that priority? Right, Deepak, are you still
okay.
there?
So yeah, I mean, in our work, we didn't address this dynamic portion, but we did consider the weighted case where each node can be given a weight. Now, that was static in our case. You can make
Okay,
that weight
okay.
as a function of time.
But then what would change in your formulation if we change it as, if we add this dynamicity?
Uh,
I mean, it's okay. I'm just
I'm
trying
not
to.
sure if
Uh,
the proofs
it's
would
very
hold in
relevant
that
to
case. I
some of
mean,
the research work that we are doing. So I was just trying to see if that has been thought through.
okay. So I can share you the preprint of this work. I'm
Okay,
not sure if that proof would hold in that case.
okay, okay. Cool,
Like on top of my head, I don't think it holds.
cool. That's
Yeah.
fine. Thanks, Deepak. Any other questions
Hey, Deepak,
from
I have
students?
one question.
Yeah, Sujit, sure.
Yeah, sorry that only we guys are asking the questions, but yeah. So, so do you allow multiple agents to visit the same node, or is it only one guy is allowed to visit that one?
Any agent can go anywhere. We assume a connected graph. So
No, so in your recurrent path that comes out of it, right? So in a
yeah,
multi-agent setting, do you have same nodes being allocated to multiple agents so that your total time to revisit is reduced, or is it like only one particular cycle that only one agent will be able to do? Do you have any such constraint?
okay, sir. So if the objective is maximum idleness, like minimizing maximum idleness, we have another result which shows that you will basically partition the graph. That is the optimal way. So in that case, you won't have. I mean, the agents would visit the same node in a staggered manner. It won't visit simultaneously.
Okay. The other thing is, how do you extend this to, let's say, that a different set of agents, heterogeneous agent system?
Okay,
That,
so the epsilon optimal proof holds for heterogeneous agents. Heterogeneous meaning each agent has a different traversal time. So that proof we have. But in terms of, let's say, battery constraints and stuff like that, it's not considered. I mean, that would still be,
okay, cool.
yeah.
Thanks.
Yeah.
Are there more questions? Okay. If no, then let's thank the speaker. Thank you, Deepak, for the talk.
Thanks, Deepak.
Thank you very much.
Thank you.
Thank you.
Bye.
Thank you all for joining.